refresh again, since we haven't really worked with HYSYS so much yet. Just do some refreshers. Okay. So what we're going to do here is we're going to set up a system where we just have two components. Okay. We're going to use benzene, toluene. We'll add benzene and toluene. I will tell you the fluids package that you should use, the thermodynamics package. This time we're going to use Peng-Robinson. And just a note on fluids packages. These fluids packages, thermodynamic properties packages, these are component specific. Okay, so if you were trying to run something like, I don't know, something unusual, like a biomass pyrolysis separation process or something like that, where you have lots of oxygenated molecules, phenol, who knows, alcohols, things like this. Some of these packages are not going to have the properties that you need to simulate that effectively. Okay. Usually they pop up a warning if you select a package that is not appropriate, it doesn't have activity coefficients within it for those components. Sometimes it will just kind of go on for you and you'll have to check the coefficients. So this, yes, binary coefficients. This is actually where you want to look. If this is just not for the exam, just for your own edification. Just in case you ever start using this for doing things that are not very much focused on petroleum, because really that's where this is really focused, is petroleum. If you start doing anything else other than that, you want to check these binary coefficients. Just make sure that these exist. Okay, so these binary coefficients don't exist, then all of your thermodynamics calculations are going to be wrong, or by default some value that is completely meaningless. Okay, so check that. Okay, so let's do fluids package. Okay. So again, we're just doing simple stuff, just benzene and toluene at this point. And the nice thing with HYSYS is it is a real-world, more exact check to this more approximate approach, right? So that hopefully is a hint that you captured. Didn't. Talk to your friend.
Will the exam be a binary system?
Yes, yes, all binary systems. Yes, we are not doing multi-system, multi-component. All binary. I mean, you can't do K-Feely with multiple components. I'd be pretty impressed if you can. If anybody can do that, I would be impressed. Wouldn't get you an A in the class. We can discuss it if you can make it, interesting. What happened there? Okay. Okay, so we just completely lost that simulation for some reason. So again, benzene. Package, again we're using Peng-Robinson. Okay, so let's just produce something that is potentially similar to what you would be seeing on the K-Feely diagram, right? So that. Right, so our classic XB or XB and XD. 0.9, 0.1. Please check these, okay? I know we use these values quite often, but these can be different values than 0.1 and 0.9. Okay, so please read those carefully in the problem statement. So let's just kind of simulate what we're doing here in the K-Feely diagram. So let's say our feed is, I don't know, 40% benzene. ZF would be 4. Just call it a saturated. Actually, let's do more complicated. Let's do half vapor, half liquid. Composition. So we're going to use 40% benzene. Let's say 60% toluene. Here we're just working in mole fractions. Conditions. Okay, so we're going to say that this is all liquid, using saturated liquid. Let's say the pressure is 20 psi. Actually, let's go up a bit, 50 psi.
Do you give us these numbers in the test, or do we just say, you know, 20 psi?
You will be given what you need. Because keep in mind, a lot of these variables are connected, of course, right? So you just can't randomly choose temperature and pressure for feed, right? You can choose one and a vapor fraction, and the other one is going to be constant. Right? So for this example, we're just going to use 50 psi. That gives us a temperature of 290 F. Make sure you check your units, please. Check your units, okay, in your simulations. Make sure you check your units, okay, because everything will go forward just fine. It won't complain, and your numbers will be completely wrong unless you check your units. Okay, so flow rates, let's just use 1,000 pound-mole per hour. We've got a nice, well-defined stream. Now the question is, we need temperatures and pressures, right? So let's go to our component splitter. Put in our stream 1, E1, E1. Okay, so here we're just pulling off saturated liquid. That's usually what you want to do if you're doing total condenser. Temperature is usually defined by house cooling water, right? So we're going to use 120 F, but we'll see problems that come with that here in a second. Let's define our composition that we're targeting, right? This is our target, right? Our target is 90% benzene in distillate, and the remainder being toluene. Not 1, 2, 2. Okay. So you see what choosing such a low temperature to condense to with these types of fairly volatile molecules causes, right? Extremely low pressure. So that could be problematic. Make sure you're watching these things, reality checks, right? So let's go ahead and bring that up to something a bit higher. 200 F. So now at least we're above atmospheric pressure, 20 psi. Okay.
How are you able to change that?
So we're changing the pressure by changing the temperature of the condensation.
We did not column or the mass?
This is at the stream. Okay. So we've chosen 1 degree of freedom to spend, which is to say that this is all liquid. Right? And then now we are choosing what our cooling liquid is. Right? Naturally, you would use cooling water, house cooling water, 120 F. That produces too low of a vapor pressure, too low of a pressure. So we bump that up to 200, and the pressure comes along for the right. Okay. Again, keep in mind, blue values are specified, black values are calculated, red values are potentially problematic or just simply assumed. Okay? So let's just assume, what do we choose? 1,000. So let's say, what would be the balance of that coming out? 40,400. 90% of 400. Something like 330. 330? Okay. So the point here is that you've calculated a value that you need, right? Which is the condenser pressure. Right? You've set the vapor fraction, you've set the temperature of the cooling water. That gives you a pressure, and you need that pressure so that you can estimate your temperature down in your boiler. Okay? So at this point in time, you don't necessarily know how many trays you're going to get. Okay? I know how many trays that we're going to get because I just did this. But let's say we approximate it at 10 trays, at 2 psi per tray of pressure drop. Right? That's 20 psi of pressure drop. So that would make this 40 psi. Boiler. Again, we are going to set, so that's a degree of freedom that we've spent. We spend the degree of freedom on vapor fraction. Of course, we have to tell it compositions. So compositions are going to be 10% benzene, 10% benzene, 90% toluene.
Did you change any parameters on the splitter that allows you to operate these?
Nope, the only thing here, we're just connecting up flows. So some of these parameters can be adjusted within here. You can adjust these here. You can adjust these parameters in multiple places. Okay, that is dangerous because you don't want to specify them in multiple places. Okay, and actually that's a good point now that reminds me, make sure if you ever get an error where it says consistency error or something is an issue or something like that, make sure you check the red light, green light things up here. Okay? Because as soon as HYSYS encounters a problem that doesn't allow it to calculate, it stops the calculations and puts the simulation into holding. Okay? And if you don't notice that, you can go on and try to do the problem and nothing will be calculating, and it will actually allow you to overspecify the problem very easily. Okay? So let's just show you what that may look like, right? So let's get rid of this cooling water temperature. And now we have 2 degrees of freedom here, right? Temperature and pressure, but the solver is stopped. It's not actually running. Okay? So let's just drop in a temperature, and you see now the pressure is not calculated. Right? And then you could just say, well, I need a pressure, right? So let's just throw in a pressure there, right? Okay, let's say you get that far, and then, well, let's just start the solver, right? Now you have an inconsistent calculation. It actually allowed it to calculate, which really what that did was it sacrificed this degree of freedom for calculating energy flow rates into the system. So you have to be very careful to not overspecify your system. In this system, you're not really specifying things in multiple places. When you're dealing with a more complicated simulation like a quick column or a full column, really in the full column case, you can have consistency problems. Okay, it'll pop up a window that says this variable has been specified in 2 locations, the calculated value or the specified value are not in agreement, and it will stop the calculation. Okay, so be very careful with that. So make sure that you are continuously running in solver active mode. Okay, because that is really where you catch these problems. So you see, as soon as we deleted that pressure, it actually calculated without an error showing it all. Okay, so be careful with HYSYS because it will kind of just do what you tell it to do, even though it's wrong. Okay, so check that the solver is active. Okay. So effectively, we have what we need out of this splitter. The only thing you are using this splitter for is to get the bottom's pressure, the top pressure, and the bottom temperature. Okay? And the condenser pressure. Right, so what we're getting out of this, we are setting our cooling temperature. That is calculating the condenser pressure, which is 20 psi roughly. Using the pressure drop approximate across the trays, which you don't actually know yet, but you could actually potentially get that from somewhere else. That's effectively all we need from that little guy. Right, so let's go ahead and get this into a shortcut column. One thing that I would highly recommend doing is not copy and pasting. And if you do copy and paste these things, change the string name after you paste it. Okay? So now let's go to a shortcut distillation column. Okay, we're using liquid top product. Our inlet is 2. Make sure you're labeling these flow rates with some distinct names. not like apples and bananas. Makes it a whole lot easier if you would like points. Okay, so once we have that, parameters, right? So now you're only dealing with two components, right? So how would you actually decide what the light key and the heavy key are?
You're gonna tell us?
Nope. Are you engineers or are you not? Right? How would you find out what the light key and the heavy key are?
Relative to
Right, exactly. Just look up the boiling point. Right? It's that simple. Right? Think for yourselves, guys. Real world is really close. Okay, so light key, right? Benzene is lighter than toluene, so we know that benzene is the light key. Toluene is the heavy key. So what is the light key in the bottoms concentration in this case? Say it loud. Right, it's just that value. Right? That's it. It's that simple. Some of these answers are quite simple. So light key in the bottoms, 0.1. What is the concentration of the heavy key in the distance? 0.1, right? Okay, condenser pressure, we had something around 20 psi. We chose 40 psi, guessing around 10 stages, 2 psi for your pressure drops. So now we have pretty much everything specified, so now we have a minimum reflux ratio calculated. So of course, external reflux ratio, we're just going to use the classical 1.3. What's 1.3 times 1.7? Get that number? 0.26. Okay, there you go. Simple as that, right? So now with all of that information, now you can actually determine your performance, minimum number of trays, actual number of trays. Actually, we got it fairly close, 10 trays, right? Optimal feed tray. Okay. So now that you have this information, so consider approaching a problem that you don't know what the number of trays are. Okay? So now that you have this, now you could actually go back and refine your answer in your splitter and say, this is the actual number of trays, and this is the actual pressure drop that should be there, and then rerun the simulation for your shortcut. Okay? Okay, so what do we need out of here? We need number of trays. Call that 13. Optimal feed, 7. We also need flow rate, right? Actual flow rate, 375. Because remember, again, we just chose what that flow rate should be, just by an approximation. By taking 400, because it's 1,000 feed, right? So we have 400 pound moles per benzene coming in. That's going to be 90% roughly of that. 10% of it's going to come down to the bottoms. So we just ballpark that. Okay. But now you have the actual feed, right? This is another value that you go back into your splitter and make those calculations more exact. Okay.
Did it change the bottom's flow rate also?
It should have, just by default, balance. Okay. Okay. So let's move on. A few minutes left. Okay, let's go on to full column. Again, change those names, those streams, please. And if you run into problems that you just can't figure out how to fix, start over. Okay. I know that's not necessarily something you probably want to hear, but unfortunately, that's what you have to do sometimes with HYSYS. Actually, some person was in my office working with HYSYS. It was just bringing some random stuff from some previous calculation, and it wasn't working properly, so we literally had to just restart HYSYS. HYSYS is not perfect. It's written by people. People are not perfect. People like you could actually be writing the next package for HYSYS. Okay, So let's go ahead and set up our column here. How many trays? We had 13 trays. We're going to send in number 3. Tray is 7. Feed. We're going to use a total condenser. Again, we're going to use distinct names for our energy streams and our products. Boiler is always the same. Condenser pressure was 20.3. We're going to use 2 psi for our pressure drop and boiler drop, and then 40 psi for our boiler pressure. And then the liquid rate was 375, and the reflux ratio was what? 2 something. Was it? 2.6. Set and run. There you go. That. Magic. So now we have a full simulation. Now we can see the error between doing something approximate and actually doing a real calculation. So did we actually get 0.9? Pretty close. Right? Probably a similar deviation in the bottoms for the composition. Right? Pretty close. Not bad. Let's take a look at some of the things in here. Again, remember, within these option panels, you can specify things. Anything that's blue inside of here, you can specify. Okay, so just be careful of what you're over-specifying, especially if you have the solver holding. Okay, because it won't complain. It will just go forward. Okay? Sometimes it complains. Best case scenario is it complains. Okay, so a few things that you want to take note of. So if we come over to performance, plots, let's just take a look at flow rates. So this is a very simple system, right? Just binary components. We have an assumption where you have constant molar overflow. This is where you can see that, right? This is also where you can test that. Okay? You can see that the ratio between your liquid and vapor is roughly constant in your stripping section and your rectifying section. It changes right where the feed changes, or right where the feed is at. Obviously, getting these numbers is not as easy to do some sort of a calculation to compare with something like the values that you're calculating here. Okay. So you can actually just do a view table. That'll give you actual values that you can plug in and calculate slopes for your upper and operating line that are being calculated by HYSYS. Okay. So you can just copy and paste these. Copy, paste, it works just fine. Like this. Paste that into Excel, use that to do some calculations. Okay. K values. Remember that in the assumption of doing this construction, we were really working with K values and alpha values, the ratio of K values, that don't necessarily change by much. So the question is that actually valid? So you have 2 K values here for each of your components. As they change going up the column, you can actually calculate alpha values by getting those values. So if you're not capturing what I'm hinting at, HYSYS is really going to be used to check the validity of a McCabe-Feely diagram, or McCabe-Feely approach. Okay. Flow rates, equilibrium, operating lines, stages, minimum number of stages. All of these things you can get from here, and you can get from here. Okay. Just a note on efficiency. So let's say if you were throwing a curveball and I said, okay, well now you have to calculate this with 80% efficiency. Remember that you can do that exact same thing in here. Parameters, efficiencies. You can just add your efficiencies just like this. You could even add them for select sections. Right? Let's say you were sold bogus trays and you just happen to get half of your trays to be bogus and half of them that work just fine. That's how you would potentially implement it there. Question is, how would you implement it here? You should be able to answer. What if you just had one tray failure, right? What if one tray just became really garbagey, clogged up, or I don't know, paper flow paths were stuck, or you had some fouling or something like that. Right? Think about it. How would that actually affect the system? How would it translate? Okay. What else? I don't think we're going to be doing any side operations. Multiple feeds and side streams, right? So let's just take a look at how easy it is to add multiple side streams. So let's say you were adding, I don't know, a liquid side stream. You effectively just come in here, add a liquid side stream, let's call it LS. Where does it come out, right? You have to determine, tell HYSYS, where is it coming out in your system? Where do you want to put it? At which tray? Okay. You just select your tray. Let's take a look at composition really quick. Let's say for some reason you wanted to pull it out at tray 8, I don't know, to get roughly 40%. Let's do tray 7, 40%. Actually, you wouldn't want to do that because that's your feed, right? Let's say 10, just for shits and giggles. 10, okay? Just like that. Reset, run. Right. So again, remember, now you have introduced degrees of freedom, right? And HYSYS obviously can't go forward until you've satisfied the number of degrees of freedom that are necessary to do the calculation, right? So what did it complain about? Flow rate. Right? Exact same thing that your McCabe-Feely diagram is going to complain about, right? You need a flow rate in order to go on. Right? So you could potentially determine a flow rate here and then put it into your simulation. Let's say, I don't know, 50 pound moles per hour. Let's make it a little higher. 100. Like that. Converges just like that. There's your liquid side stream. All of this is effectively determined. Why? Because it's basically just coming right out of the column. Right? All of those values are determined by the equilibrium in your column. Right? Here's your composition. Okay. Okay. So, any questions